Bismillah ar-Rahman ar-Rahim wa salatu wa salam ala ashraf al-mursaleen. Thank you so much for this presentation. Really, I'm very glad to be here in this symposium, and thank you so much for the invitation from the General Director of Gabes and the Chairman of this symposium. Thank you so much. Thank you so much again for Professor Fawzia and Professor Jamila for the hospitality. My contribution is about characterization and effectiveness of novel nano-biosorbent from clay, mineral, and solid waste. This work is in collaboration with Professor Abdelkader Waqwaq from the University of Ouadsouf here in Algeria, and my student Dr. Imena Amri, Asia Ben Amr, and Iman Fallah. The philosophy of this presentation is coming from the natural materials and solid waste, and in order to improve the propriety and the characteristic of these materials, we can modify this and synthesize novel materials like to adsorbent. With these novel materials can be have a high performance and functional surface, high adsorption capacity, and high surface area. In this presentation, we will present three case studies. The first one is geopolymer alginate, is the composite number one. The second one is about zeolite and activated carbon, and the third one is about nano or organonuclide composite with the bismuth phosphide. I start by the first composite is geopolymer alginate. This is in collaboration with the National Center of Research on Material Science in Tunisia and the University of Seville in Spain. The question is, what is geopolymer? Geopolymer are formed by reaction of alkaline reacting with the source of aluminosilicate. Source here is the clay minerals. Mixed with sodium hydroxide or potassium hydroxide and added the water in order to obtain geopolymer paste. In general, we have two states for the geopolymerization. The first one is the solution of the aluminosilicate. The second one is the polycondensation, and this reaction can be at room temperature and at high level temperature. In our study, we have used the ratio of silicon and aluminum about 2 because we have illithocaulinitic clay from Tunisia, and the application can be for the environment application in general treatment of water and wastewater. The clay used in this study is from Tunisia, from the south, exactly from Medellin, is illithocaulinitic clays, and in addition, the impurity is quartz. About 20% of quartz in this clay mineral, and the chemical analysis give an idea about the composition is more than 50% of silicon oxide. Aluminum oxide is between about 14, and iron oxide is about 8, and the percentage of the potassium oxide is related to the existence of the light. Now to move to the preparation of geopolymer, first crushing and screening the clay mineral, after that the calcination at high temperature about 100 degrees C or 90 degrees C, addition of the sodium hydroxide or potassium hydroxide with a high concentration, more than 10 molar. After that, mixing the mixer, and we can prepare two types of geopolymer. The dense one is in general cement or concrete, but the second one is very porous geopolymer, is named the foam geopolymer when we add silica fume. The characterization now, the characterization by scanning electronic microscope is giving an idea about the porosity and the microporosity and the macroporosity of geopolymer, and after that the first application of this geopolymer is in the water treatment of the heavy metal of copper and lead by adsorption. The kinetic is very speed, and the capacity of adsorption is very, very high compared to other adsorbent, about 55 milligrams by grams in the copper and 83 milligrams by grams for for the lead, and the mechanism is in general the activate site in the surface of geopolymer adsorb this heavy metal. Now, the application number 2 is the synthesis of composite alginate geopolymer using a syringe in the alginate and calcium chloride in order to obtain a small sphere with 2 millimeters diameter, and after that dried to the 40 degrees C. You see here the scanning electronic microscope photo of the geopolymer, and after the synthesis of the composite alginate geopolymer. This composite has been used for the adsorption of 5-fluorouracil from contaminated water. The 5-fluorouracil is used for treated cancer. They start by the pH. Like to see here, the pH when it is 2, we have a very low adsorption because this is destruction of the structure of our materials. But the pH 4 and 7, the adsorption is very well because we have a negative charge on the surface. Here is the modelization of kinetic by first order and second order. That second order is the best because the square area is about 1 and the kinetic is very, very speed, about 70% in 1 hour. Now the adsorption protocol. The experimental is firstly the concentration is about 0.1 to 20 milligrams per liter. The contact time is about 3 hours, pH 7.8, and the solid liquid ratio is about 0.02, and the adsorption are modelized by Langmuir and Friendlich model, and the maximum of adsorption is 6.2 milligrams by grams. This is a very, very huge adsorption because the problem of this pollutant is not absorbed by the mineral. The mechanism can be divided in three types of adsorption. The first one is the pore filling, the second one is the hydroxyl and carboxyl reaction, and the third one is NP interaction, and can be created between the aromatic and the structural of the pollutant. As a conclusion of this part, the synthesis of geopolymer from clay mineral waste is well mastered, and the foam geopolymer are a good adsorbent of heavy metal. And the second one conclusion is a new formulation focused on the preparation of, course, linked adsorbent lead to the alginate geopolymer has been carried out, and the particle of the composite is with low cost and eco-friendly materials that exhibit rapid and excellent adsorption of capacity of the F5FU. This work has been published in Chemosphere. Now I move to the second part, to the composite zeolite activated carbon. This is in collaboration with the High Institute of Water Science and Techniques and the National Center of Research on Material Science in Tunisia, and with the École Nationale Supérieure de Chimie de Rennes en France. This study is based on the big problem of the COVID-19 pandemic, when we have a lot and a huge quantity of waste, aqueous waste like to diclofenac, volatile waste like to chloroform DMDS, and solid waste like to wooden depressor. And the problem of this waste is not very easy to treat it in the classic station of treatment, and is create of a new high contamination site. The solution for adsorption this pollutant is to use the combination between zeolite synthesized from clay mineral and activated carbon synthesized from waste from the wooden depressor. This precursor can be used for the adsorption of aqueous and volatile pollen. Firstly, what is the zeolite? Zeolite is composed by tetrahedral. In the tetrahedral you can put silicon or aluminum, and after that we link the tetrahedral in order to secondary unit and the the three-dimensional in order to obtain the structure of zeolite A, sodalite, fugacite, for example X or Y. We use it here two clays. We have the same composition, allotokaolinitic clay, with the impurity in the first case. In the case of storagein from the Medellin clay, is quartz, dolomite, and hematite. And the second one, when found only quartz. The percentage is in the table. When use the Tejra clay, the halite is 39, kaolinite 31, quartz 22, dolomite and 2, and hematite 6. In the case of Noureddine clay, the percentage of halite is more important comparing to the case of Tejra, is about 63, kaolinite 18, and 11 for the quartz, and silver for the hematite. Now I move to the preparation of the zeolite. We mixed the clay mineral with 3 molar of sodium hydroxide and put it in the furnace for the temperature more than 600 degrees C for 1 hour and a half. After that, the step of the aging is the mixing of with the distillated water for the 24 hours, and the activation or the crystallization can be at different temperatures, 60 degrees C to 110 degrees C. And after that, the composition can be filtered and dried. Here we used 3 temperatures for the synthesis of zeolite: 60 degrees C, 90 degrees C, and 110 degrees C. And in any case, we used 3 times, 4, 8, and 24 hours. The characterization now for the zeolite, we used the case of temperature 110 degrees C. We found that at low time, 4 times only in the case of Tejra clay, we have amorphous structure, but after 8 hours, we have zeolite P. In the second case of the Noureddine clay, we have zeolite X. The fugacite pure is a very interesting result. And this structure can be maintained for the 8 hours, but after 24 hours, we move to the HS zeolite. Here is the CUC, the cationic exchange capacity. We move from the halite or from the clay 17 milliequivalent by 100 grams to 313 or to 260 milliequivalent for 100 grams. This is a very huge CUC comparing to clay minerals. The crystallinity is very high of the different zeolite synthesized. Here is the particle is very clear and have a rectangular or cubic form, and the HS is the same, and the X is more developed, and the cavity is very high comparing to the other. Now the preparation of activated carbon using the waste of the wooden tongue, the depressor. Firstly, grading the waste. After that, added the zinc chloride and activated at temperature 550 degrees C, washed and filtered, and after that dried at 80 degrees C for 12 hours in order to obtain the activated carbon. The characterization by scanning electronic microscope. give idea about the porosity, is the canal porosity, and in the canal you can find very nano pores. The specific surface area of this activated carbon is very higher comparing to the commercial activated carbon, is about 1,511 square meters by grams, and the porosity is, the majority of the porosity is micropore, and is a very, very surface area developed in this new material. Now, the preparation of our composite zeolite activated carbon by sample mechanical incorporation of 30% of activated carbon with 70% of zeolite P. Like to see here in the scanning electronic microscope, we put the activated carbon in the porosity in order to react it with polluant when we adsorb any polluant used. The adsorption here is the diclofenac. The diclofenac is an anti-inflammatory medicament. It's very used in the period of COVID-19. And the experimental study is the quantity or the mass of the adsorbent is about 0.1. The volume of the floconate is 30 milliliters, and the speed is 250 rotation by minute, and the analysis can be used by the UV spectroscopy. The other term of the adsorption compared to the clay minerals, this is the adsorption of clay minerals, and the both is the zeolite P and the zeolite X. The adsorption capacity is very, very huge comparing to the clay mineral. Here, for example, the clay mineral T or the clay mineral D, we have only 90 milligrams by gram, but in the case of zeolite, we reached 290 or 308. We move to the adsorption of the volatile organic compound, the chloroform and DMDS, using the characterization by the gas chromatography, using a syringe with a volume of 500 microliters. The adsorption, the isotherm adsorption compared to the zeolite in this case, this is the zeolite, this is commercial carbon. This is zeolite, it is a composite zeolite activated carbon, and this is activated carbon synthesized from the wood. We observe that the quantity or the adsorption is very higher for the synthesized carbonate, and after that for the composite zeolite activated carbon. The same in the case of the DMDS, but here we have the same adsorption quantity for the synthesized zeolite and the composite zeolite activated carbon. Here is the modelization using the both model, Langmuir and Freundlich. Langmuir is the best, and the quantity is more than multiplied by 20 for the case of chloroform, and more than 10 in the case of DMDS. As a conclusion now, the mineralogical characteristic of the Tejra and Douiret clay enabled rapid successful synthesis of faujacetate X in only 4 hours, and zeolite P only for 8 hours. By the alkaline fission with the capacity or the exchange capacity is very higher, more to 200 milliequivalent by 100. The second conclusion, the faujacetate zeolite absorb maximum amount of diflaconate equal to the 308 milligrams by grams, and comparing to the clay mineral Tejra and Douiret is very low comparing to the zeolite. In the second case, when we use the composite activated carbon and zeolite, in the case of the adsorption of the FU, the 5FU, we found that the surface is very higher, about 1,500 square meters by gram, and the capacity of the adsorption is very, very higher comparing to zeolite. Here is published in two famous journals in the environment. Now, the last part, is the organoclay with the bismuth phosphate. This is in collaboration with the National School of Engineering in Gabes, High Institute of Water Science, and the University of Milano in Italy. In the case in general, the big problem of the pharmaceutical wastewater, the adsorption used can be very high porosity and very functional surface. The big problem of the classic adsorbent is the slow kinetic and low adsorption quantity. For this reason, we can use both the adsorption and the photocatalysis in order to increase the degradation and the adsorption of our pollution. We use clay mineral, exchanged with the sodium. After that, we added nanoparticle or tensioactive on the clay, and after that, we obtain a composite material, nanoparticle, clay, and tensioactive. Is a very, very famous nanomaterials used for the adsorption in general of the pharmaceutical compound. The synthesis processes is firstly, we use the clay in the sonitated for 20 minutes. After that, we mixed both composite in order to obtain the bismuth phosphate, the nitrite phosphate with the 0.3 molar, and the 2 hydrogen sodium phosphate for the same concentration. After 2 hours, we can put the solution in the oven for 100 to 20 degrees C for 1 night. We obtain the clay bismuth phosphate. When we add the HTDMA, is the tensioactive, and we make a treatment by microwave, we can obtain the composite HTDMA, clay, and bismuth. The characterization now by diffraction, by X-ray diffraction, give an idea about the modification of the structure of our clay and the composite. Here we use the clay number 1 is M, the clay from Marnia, from Algeria, from here. And the second one is the smectite from the Gabes, from the Tunisia. And when we have modified clay by the bismuth phosphate and by HTDMA bismuth phosphate, we can find that we have this peak is disappear. Why? Because the bismuth phosphate nanoparticle is in between the Montmore unit layer. The characterization by the specific surface area give an idea about the decrease of the surface area, because the nanoparticles are put in the porosity and blocked to nitrogen, putting to the microporosity and nanoporosity. The surface area of a clay was dramatically decreased because the increase the insertion of the bismuth phosphate inside the pore. Now the photocatalysis and the adsorption combined here in drag firstly, after that in the UV photolysis and LED photolysis, and after that in the solar or light solar photolysis. You can find that in this both case, UV and solar, the adsorption and the photocatalysis is very higher, and the ratio C on C0 is about very 0.1. Here the study with the concentration, the first one, 10 ppm to 50 ppm. Second, the study with the percentage of the mass from 0.25 to 1, and for the both here is the comparison between the nano composite Montmore unit bismuth phosphite, or when we add the tensioactive HTDMI Montmore unit bismuth phosphite, and the same for the case of when we change the Montmore unit by the SMICTIT, we can find that the adsorption and the photocatalysis, the removal is more very high when we use the solar light compared to the drag. This result is very interesting for the adsorption of the defluconate like to pharmaceutical pollutant. And the conclusion of this part, the HTDMI in the composition of the composite HTDMI Montmore unit bismuth phosphate has a positive effect on proven further the adsorption ability of the photocatalytic, and the defluconate was removed mostly by physical adsorption. Second conclusion, this study show promising result in enhanced adsorption and photocatalysis ability of clay bismuth by sustainable and sample surface modification. The sample modification of the Montmore unite bismuth composite by the HTDMI significant both the adsorption and photocatalysis effects with the solar light. This is very interesting because we use only the solar light to remove the defluconate from water. This result or this work was published in two famous journals in the domain of water treatment and catalysis. And thank you so much for your attention.
Many thanks, Professor Hamdi, for your great talk. We now allow our invitees to ask questions if they have one. Any questions?
D'abord, nous vous remercions pour la présentation. Étalée sur 3 parties, vous avez testé tous les phénomènes explicatifs de l'absorption et de la catalyse. Ma première question par rapport aux géomatériaux de la première partie. Donc, pour la première partie, c'est-à-dire à travers les résultats, surtout avec la rétention et l'absorption des métaux lourds et certains métaux toxiques, quel sera le devenir de ce matériau après donc, la décontamination ou bien après la rétention de ces matériaux?
Ok, donc vous voulez... Les matériaux utilisés pour l'absorption vont être donc utilisés où?
Non, c'est-à-dire que par la suite, une fois qu'ils sont désactivés par les métaux lourds, comment on va gérer la suite de ce matériau en tant que déchet?
Ok, donc il y a deux procédures. Soit on va miner ces produits-là dans le centre de traitement ou bien le centre de stockage des déchets. Soit la deuxième, la procédure qui est utilisée actuellement, c'est d'utiliser ces déchets-là directement dans la cimenterie pour la production de ciment.
Elle a été déjà testée?
Oui, oui.
Pour la deuxième question, quand on associe la géolite au charbon actif, on doit s'attendre à la diminution de la surface spécifique.
Ouais.
Pratiquement, pour les charbons, ça avoisinant de 2000 mètres carrés par gramme, donc on se retrouve vers 1500, alors que si on prend le charbon actif seul, dans certaines dépollutions, il est efficace, mais le grand problème, c'est que le charbon actif il est difficile à être régénéré.
Ouais.
Est-ce que la zeolite est associée à ce charbon actif de façon aussi à réfléchir sur la régénération de
Oui.
ce matériau hybride.
Oui, premièrement, donc la régénération, mais deuxièmement, c'est la stabilité thermique. La zéolite peut être donc vraiment utilisée à haute température et comme ça, donc lorsqu'on a donc le charbon à l'intérieur du zéolite, on va protéger le charbon de telle manière qu'il ne se dégrade pas. Il absorbe même à haute température.
Merci.
Merci à vous.
Any other questions?
Merci, professeur.
Merci à vous.
Bienvenue, monsieur Nathalie.
Merci.
Merci de votre communication enchaînée sur 3 parties. Je voudrais savoir, vous avez dit qu'il y a un ajout au niveau des ciments.
Ouais.
Le pourcentage que vous ajoutez.
Bon, généralement, la quantité de ces géopolymères ne sont pas tout à fait vraiment intéressants hein, comparativement. Donc, ils ne dépassent pas le 2%. Voilà. Oui, oui, c'est au niveau de crude, au niveau de l'entrée. Oui, oui. Oui.
La composition calcaire.
Oui, calcaire, argile à titre d'exemple. Dans le cas des argiles, on peut utiliser ces polymères-là vu que la même composition, oui, c'est la même composition aluminium-silicium.
Vous obtenez quel ciment, quel type de ciment?
Bon, dans ce cas-là, c'est le ciment Portland. Oui, mais on peut utiliser le géopolymère comme ciment tel qu'elle est. Donc, mais il fallait vraiment tester quelques paramètres et on peut vraiment utiliser le ciment géopolymère actuellement. C'est la mode en fait. Donc, d'utiliser ces polymères-là, les polymères minéraux, comme des ciments. Voilà.
Merci.
Merci à vous.
Thank you very much for an interesting presentation.
Thank you, sir.
So the problem of removing drugs from wastewater is a major one and increasing. Can you compare your solution with biodegradation methods where microorganisms are used to break down the drugs? One of the reasons I'm asking is I worked for a while at a pharmaceutical company, and they had their own wastewater treatment plant, and they noticed that initially the microorganisms in the wastewater treatment plant could not degrade the compounds that were synthesized on site, but after a certain time, they saw the emergence of microorganisms that actually could degrade, probably due to some selection process. So can you comment on the biodegradation as an alternative to the process that you have developed?
Yes, I think biodegradation is a very famous technique used for the degradation of the drugs, but the problem is the kinetic, firstly, and the temperature, because here in the north of Africa, the temperature in the summer can be about 50 degrees C, and the bioorganism can be not can be dead in this condition. And in the case of the use zeolite or use geopolymer, we use activated carbon combined with alginate or other, the kinetic can be very, very, very rapid and very speed, about 2 hours, and we have a maximum of absorption, and we can use it at high temperature. Okay.
Thank you, Professor HAMDI, for your presentation, interesting presentation.
Thank you.
I have just one question.
Okay.
Did you test your zeolite activated carbon hydride materials in various Western samples?
Various?
Various.
Yeah.
Various wastewater samples.
In this case, we use it only for the drugs, for the diclofenac. But actually, I have a student work in the pesticide, about absorption of the pesticide by this composite, and I think is very absorbent for the pesticide, herbicide, and the pharmaceutical compound. Yeah.
More questions? No? Thank you very much, Professor.
Okay, thank you so much.